There we are. We're on part 3 now of the urinary system on page 961. And we had just left off here looking at sort of a close-up here. This is basically a microscopic view. You can't really see very much here in the kidney. But at any rate, we do have the arcuate artery coming across here. This is the arcuate artery, the arcuate vein. Everything from here down is medulla. Everything from here up is cortex. We have, as you can see here, the radiate artery, cortical radiate, and it's coming over here. And we're going to be getting, let's go to this one, an afferent arteriole coming in, fenestrated capillaries, and then the efferent arteriole exiting. So we have a high pressure system here, and essentially everything that's liquid in this area, or a lot of what's liquid in this area, is going to be basically dropped off here in the very beginning of the nephron. This is the Bowman's capsule. This is the proximal convoluted tubule. We go on. Notice that the efferent arteriole, which functions in terms of pressure as an arteriole, and then quickly becomes capillary network. Up here we have the paratubular capillaries, paratubular. Down here we have a set of capillaries that are referred to as vasa recta. Okay, so at any rate, wherever we have tubular structure here, where we're going to gain or lose something in the way of nutrients or electrolytes of some kind, or possibly other molecules of some type, they're going to be leaving the bloodstream mostly here, and then re-picked up again on the other side. That which is not needed, whether it's the urea, it's maybe excess water, there may be other excess nutrients. I take a lot of vitamin C as a supplement, so I might be having expensive urine, right? So not all of the, not every single one of the essential nutrients will be taken back up into the blood. So you have to think of this as sort of a duodenum here. We've been through the science of the duodenum and how things work there. Here we already have monomers because we're already in the blood, right? So all we're doing really here is cleaning. And we're taking back up. We're basically dumping the blood out, the liquid portion, and we're taking back up the water and the electrolytes, and everything that's essential is coming back into the blood again. One of the things that we could do, of course, is that we could secrete bad things in the blood in here, simply because it doesn't leave fast enough in the filtration process. We'll get into that a little bit later, but that's also a possibility that you might want to keep in mind for later. The proximal convoluted tubule here is the most complex part of the system. It is the system most akin to the early parts of the small intestine in terms of uptake of nutrients in a very, how shall I say, wholesale manner. Okay, so this is a little bit like a Sunday afternoon color comic episode here, where you sort of follow the proximal convoluted tubule, see if you and your siblings or whatever they're laying on the floor can go through the color comics and follow the little diagram here. Anyways, so that's the idea of what is the proximal convoluted tubule. This is a very old diagram that they keep re-updating. Technically, we're supposed to be having not the distal convoluted tubule coming close up here. We're supposed to actually be having the ascending loop of Henle coming up right up against the Bowman's capsule there. So that's something that some new artist is going to have to come along and create, because they keep reusing the old art, and it's not actually accurate. But we'll get into that more in a moment. Anyways, what we're doing here is this is just all basic stuff that we've looked at before in the digestive system. I've added a few little things here. For instance, when you're out on a long distance run, or you're in the summertime on a hot day and you've, how shall I say, taken a walk in the park for a long time, didn't bring any water with you, and here you've perspired, and now in your perspiration there's a lot of salt that leaves in your perspiration, and you need to spare the salt. How are you going to get that salt back? Is that the kidney is going to spare it under the influence here of aldosterone. So aldosterone works on, and let me make this really clear, the chief cells of the cortical collecting duct. Who are the chief cells of the cortical collecting duct? First of all, here's the collecting duct. Let's run through the nephron briefly. Here we have the proximal convoluted tubule. We have the proximal convoluted tubule, if we follow it carefully, ends over here. It comes down. This is the thin portion, which is a downward portion. And then, we have this correctly here. Let's make sure that this is the correct procedure. It is. Okay, and then we come back up and we go to the distal convoluted tubule. And the distal convoluted tubule here comes up this way, and then we eventually get over to the collecting duct. So we have a proximal convoluted tubule, a Henle's loop, sometimes called the nephron loop, and now we're calling this the distal convoluted tubule as we come back up again, and we're emptying into the collecting duct. The collecting duct will travel down the pyramid. The pyramid will end in a papilla and will end up in a minor calyx. The minor calyces will lead to major calyces, which will lead to the ureter, and then finally the urinary bladder. Okay, so we're getting all of our nutrients, most of our nutrients and water comes back right up here. This is an opportunity here where we can concentrate the water, and we'll talk more about that later. Here's a very long Henle's loop that is mostly medullary. Some of these loops are somewhat not as long or slightly cortical. Some loops are extremely medullary. Okay, so as I was saying before, it's possible to lose a lot of water and salt if you're perspiring and not replacing the electrolytes and water. Sometimes if you have a drink of water on a hot sunny day in the summer, it feels as though that the water is not really doing it for you, and you need to have something else, and it turns out it's the salt that's missing. Some people will have some fruit with salted fruit, and sometimes I use salted raisins for that purpose. Okay, so at any rate, you need the sodium, and you need to also sometimes potassium is also necessary to add to those sports drinks, if you notice carefully. At any rate, the aldosterone is acting here on the cortical collecting duct cells, and what's happening is we're exchanging potassium. Potassium is going to get into the filtrate and ultimately the urine, and we're going to pull the sodium out. So this is an exchange. We've seen this before in the pump that exchanges potassium and sodium in the membranes of neural cells. So this is another example of that, where we're getting rid of the potassium and we're keeping the sodium. We're doing a fair exchange, and the sodium will end up in the blood. Okay. Wherever sodium goes, however, also water can follow. So another thing that we do here is that we construct aquaporins, and we do it under the influence of ADH. So the ADH causes an aquaporin to form in a fraction of a second, actually, we can make these. And then water from the filtrate goes out, selectively goes out. Sometimes it brings some urea with it, but mostly it's just the water. We'll talk about why urea actually plays a role in the extracellular fluid out here in the kidney. It adds to the electrolyte tonicity. So we'll pick that up in our next episode.